Christmas vacation thing when we do household circuits later, probably on Monday. Right now I want to go into multi-loop circuits. Y'all good over there? Yeah, okay. Alright, so multi-loop circuits. We're going to deal with, circuits that have more than one loop in it. And when we're working with these, we're going to have two rules. We've already seen these rules. They're called Kirchhoff's rules, the junction rule and the loop rule. They're pretty simple. And so we've already seen them, so hopefully they look familiar. We're just going to give them sort of different names. The junction rule says that the sum of the currents entering a junction must equal the sum leaving the junction. There, JXN is for junction. All right, I skipped a couple pages in your book. We're going to come back to it when we do household circuits. Okay. Kirchhoff's rules. This is the junction rule. Remember we talked about this when we did resistors in parallel. That whatever current enters a junction has to leave that junction. So for example, if I have a current I don't know, equal to 12 amps, and then I have a current here equal to, I don't know, 10 amps, then I want to know what this current is. What would it be? Right, it'd be 2 amps. You can write them differently. Like that seems pretty obvious, but let's say that I have a circuit that looks like this, and I have a current, say, of 10 amps, 2 amps, 3 amps. What would this current be? And would that current be going in or out of that junction? Huh? Well, let's see. So we have, you can redraw it a little bit differently. Like this circuit is the same as this circuit with 10 amps going in, 2 amps going out, 3 amps going in. So what's that outgoing current going to be? Well, I have 13 amps going in, right? 11 amps coming out, right? So I have 11 amps going out. So these two junctions are the same. I could think about it in this way, that here I have 10 amps going in and 2 amps going out. That means that I have to have 8 amps going in this little part of the circuit, and then I have 8 going in and 3 going in, so that means I have 8 plus 3 or 11 right there. All right, so you can see a multiple choice question along those lines on the test. All right, and then we'll also need to use the junction rule when we're dealing with multi-loop circuits. All right, the second rule is called the loop rule, which we've already seen. It just says that the sum of the potential differences that's delta V. Yes, sir. The sum of the changes in potential across all the elements around any closed loop must be 0. Just the sum of the potentials across a loop equals 0. We've seen this already, where if we have resistors in series, I have a certain potential here, and then across each of these I have potentials. This is going to be a positive potential, and here I'll have a negative potential there, and a negative potential there. If I add all those up, they'll equal to 0. So what I would see was that V minus V1 minus V2, that's all equal to 0 when I add up the sum of those. We'll have some guidelines about what are the potentials across resistors and across batteries, whether they're positive or negative. All right, that's called the loop rule. We've already seen that, as I said, with series circuits. Okay, so here we have a few guidelines. When you're going around a loop, a closed loop in a circuit, you'll need to decide whether the change in potential across a resistor is negative or positive. And we'll have 4 little guidelines for you to know about when you're going across a resistor, is the change in potential positive or negative? And when you're going across a battery, is it positive or negative? We'll have two directions that we have to consider. The direction of the current and then the direction that you're traveling. These are just directions that you pick. It doesn't matter what you pick for these directions. It's just something entirely that you just, pull out of your head. The direction you're traveling and then the direction of the current. So let's imagine I have these resistors. I'm traveling from point A to B. You'll see what I mean by that in just a bit. But when we're going through a loop, that means that as I'm considering each element, I'm going in this direction, going from point A. And let's imagine here that our current on this first one is in the same direction as what we're traveling. So here is I. The change in potential across this resistor is going to be negative IR. However, if we consider the same resistor, but going in this direction, all right, so we're still traveling from point A to B, but now the current is going in the opposite direction. So there's two directions. We're going in this direction, but the current is going the opposite direction. What do you think the change in potential is going to be for this resistor? Positive or negative? It's positive. The way I think about this is, resistors, the way you're supposed to think about them is if you go with the current. And so resistors are supposed to have a negative change in potential, a drop in potential. So when you go opposite the current, then you're going to have the opposite of that, which is a positive change. So delta V here is equal to positive IR. Similarly for batteries, we have some rules. If we have a battery and we're moving from low to high potential, like this one, moving from points A to B, so I'm traveling from points A to B. Here, the direction of the current doesn't matter. So let me write that. The direction of the current is irrelevant. Direction of the current is irrelevant. So irregardless of the direction of the current, if I'm moving from this direction to this direction, my electrons are going to experience a change in potential that's positive. So they're going to gain energy. The way I always think about this is I imagine that this is like a roller coaster. Like, when the roller coaster goes up and you have these electrons that are traveling along in the wire, and then they come to a little ramp and the electrons go up. You know what they say? They say, whee! And they gain a bunch of energy, and then they're off to go do whatever they're supposed to do. So always imagine like a little ramp there, and the electrons that come on. What do they say? Whee! Right, you have to say it like that. Alright? By the way, I was talking to my class the other day, not one people on class, we're doing sound in there. And we talking about pitch, and I don't know if I ever talked about this, but there's a thing I do with my kids. Y'all should try it. You don't have kids. No? But kids, they always get thrown off by this. Because kids, they can't do anything. They didn't do that. So, I always tell my kids, why don't you try doing this? Instead of saying low, high, like that, to do it the opposite way. Right? Low, high, and they can never do it. They'll either try it. I'll try it right now. Try it out. Low, high. See, that's wrong. Low, high. Try it again. Yeah, I can't do it either. It took me a lot of practice. Yeah, I've been practicing for a long time. So, alright, so anyway, it moves from low to high potential. Now, the other way, so this gives a positive change in potential. Alright, if I'm moving from point A to B here, my electrons coming along this way, they have a lot of energy, and then they find the ramp, but it goes the opposite direction. So they're not all wee and stuff, they're just like, oh, bummer, I lost my energy. And so here, when I'm moving in the opposite direction, I get a change in potential that's negative. Where might you have a case like this where electrons come along and they lose energy going into the battery? Why would you want electrons to lose energy when they go into a battery? No? There's not much instance for us to lose energy going into a battery. It's real practical anyway. No, this is a battery, not a transformer. That's something else. We'll talk about transformers in a later chapter. No. Well, why would we want to put energy into a battery to charge it, right? So that's an occurrence when you want to charge a battery. You would flip the lead to the battery, so you have current going into the battery. We'll see some places with that. All right, so for resistors, when you're traveling with the current, the change in potential is, what is it if you're going with the current? It's negative, right. So it's negative. If you're traveling against the current, the change in potential is positive. For batteries, when you have electrons traveling from low to high potential, that is from the negative side of the battery to the positive side of the battery, that change in potential is positive. I get a positive delta V. The electrons have gained energy. When you have electrons traveling the other direction from high to low, that is from positive side to the negative side, from the big side to the little side, the change in potential is negative. The electrons have lost energy. And when you cause high to low, that's when you charge a battery. You can also have multiple batteries. Gary, I think, sort of alluded to this, but you can have, I think it's Gary, you can have multiple batteries in a circuit, and one will be driving current in one direction, and one will be driving current in the other direction, and it'll affect the overall current. Right? So, but we'll see that in some multi-loop circuits soon. All right, let's try this one. It's a quick test. By the way, let's see, our next test, just to give you a little heads up, is April 1st, which I think is that 2 weeks from this coming Wednesday? Yeah, 2 weeks from this coming Wednesday, so just keep that in mind. We're going to start doing different things, so you know how in the beginning of the semester we sort of interjected with these chapters because I'm adding new material. We're going to be doing that too. The next chapter we'll do in the book, but then we're going to go into other things. And I know that y'all are doing optics in lab, those of you that are in lab, but unfortunately you will be doing it. I think you're starting it today or tomorrow. Huh? Good. We're not going to do it in here at all. Yeah. No, it's good for you. Oh, you're you're doing that. Yeah. So, you don't have to do ray tracing at all? You do that? Probably not in the lab, but I had to do it. Oh, yeah. All right, but anyway, we're not going to do that. We're going to do some other. All right. Let's try this question. What is the current in this circuit? So you just want to apply the loop rule. You'll need to pick a direction for the current. It doesn't have to be the correct direction for the current, but then write the loop rule and then go through and choose what is the change in potential for each element. Is it positive or negative? Like I know I'm going to get 6.6 times I here, my change in potential, but is it positive or is it negative? Here I'm going to get 2I. Is it positive or negative? So I'll get positive or negative 18, positive or negative 12, and plus or minus 1I. So when I write those, the loop equation. Y'all know where to start on this? No? Alright, let me give you a little jump start here. So I'm just going to pick a direction for the current. You might have, if you already chosen a different direction, that's fine. I'm going to say that the current is flowing in this direction. So that's my current I. And then I'm going to pick a direction to travel through the circuit. I'm going to start right here and go in that direction all the way around the circuit, adding up the changes in potential until I get back to that same point. And I know that the changes in the potential, the sum of all those, will equal to 0. So I'm going to go through, and this first element, I'll have the change in potential is going to be -1 times I, right? Because I'm going with the current, and so I just say -1 times I. And then I'll do the same here. Is this going to be plus or minus 12? Is this plus or minus 2I? Is this plus or minus 18? And is this plus or minus 6.6I? And then once I get that, I just solve for I. This isn't a multi-loop circuit, this is a single loop, but you can still use the loop rule for this. Maybe do a little kickstart? Yep. My next term is going to be positive or negative as well. It's going to be positive 12. So my second term will be -1I plus 12. And then I'm going to have 3 more terms. Plus or minus 2I, plus or minus 18, plus or minus 6.6I. And then I just solve for I. Sort of evenly split, everybody. Some of you put A and some of you put B. One of those is right. Alright, I'm just going to stop here by 6:45. I think that's everybody. 1, 2, 4. That's everybody. I'll stop at 6:20. 6:20. I'm pretty sure it's A. Let's see. So I have -I plus 12. What's the next one going to be? the next term? Minus 2i, plus or minus 18? Minus 18, right, because I'm going from high to low at there. Electrons are going down, minus 6.6i. All that's equal to 0. I can combine some things. I get negative 6 minus 9.9i, or excuse me, 9.6i. So solve that for I. That is A. It's about 2/3, which is A. I guess if you put 3, you probably chose some of your directions incorrectly. Is that what you did?
Yeah, but
Okay, yeah, you put positive 18, yeah. So you have to be careful about choosing the signs for these. Also notice here that I got a current that's negative. What does that mean? That I got a negative value for the current? That I chose the direction incorrectly. So I chose the direction here to be counterclockwise. So the actual direction is clockwise. But you probably could have looked at this because look, I got a 12-volt battery pumping current in this direction, and I got an 8-volt battery pumping current in this direction. So the equivalent of those would be a 6-volt pumping in this direction. The 18 volts going away. All right. Yeah.
why it is negative 2i.
Negative 2i because I'm going with the current across the resistor, and resistors experience a drop in potential when you're going with the current.
Because the right side is like the voltage is higher.
Huh?
Because the voltage of the right side is higher.
For the
2 ohm.
resistor?
Yeah.
Right, yes. If you want, I don't really think about it that way, but yeah, you're right. There is a negative drop in potential. That is, I imagine my electrons traveling through here, they initially have a big energy, and then they have a smaller energy when they go through that resistor. Whenever I have when I'm following the current going through a resistor, I have a drop in potential. That's what resistors do. They cause a drop in potential.
May I just add up all the resistance and add up the voltage?
You could do that here. Well, you can't add the voltage, you have to subtract them because they're opposed to one another. Right? But we're going to do multi-loop circuits and it won't be so simple because you'll have different currents that will be at play. Okay. Let's do that now. So this was a pretty simple one, but let's do a multi-loop circuit. That's one where I have 2 or more loops. All right, I have this circuit. Resistors, and I have currents. I've already labeled the directions of the current. These may or may not be the true directions of the current. They're just ones that I've picked. Now, from this circuit, I can write 4 equations. I can write 3 loop rules because I have 3 distinct loops within this circuit. What are the 3 loops? Right, I have the right loop, the left loop, and then the big loop, the outer loop. And then I could also write an equation for the I write an equation for the junction rule. I can just pick a junction and say the incoming currents equals the outgoing currents. All right, so we can write them. The left loop. Actually, I'm going to write them here next to the circuit so we can see the circuit. But I'll do the left loop first. All right, so that's going to be starting here, going here, here, and then coming back to here. That's going to be positive V1 minus I1 R1 minus V2 plus I2 R2. And that's all equal to 0. Then I can write the right loop. Let's start right here, go in this direction, go over here, and then come back to where we left off. You'll take just a second to write the equation for the right loop. Start at this junction right here, and go in this direction through R2. So that first element is going to have a drop in potential, negative I2 R2, plus V2, just like we had before. and then add in V3 and I3R3. Yeah. Okay, we know that if we're going with the current, and we have two directions. The direction that we're going through the circuit, in this case, I'm going in this direction, and then I also have the direction of the current. And in this case, the current is in this direction, so I have a negative change in potential, a drop in potential across that resistor. Alternatively, over here, look, the current's going down, but I'm going up. I'm traveling through the circuit going up. So what's the potential across this resistor? Positive, like a rise. Right? So how does this one look? I've already told you negative I2R2 plus V2. What about the next one? Minus V3 and then plus I3R3. And then that's all equal to 0. And then I can also write the outer loop. Let's start here. Let me erase all these marks that I have. Start here and go all the way around until we come back to the same part. It's going to be plus V1 minus I1R1, and then you keep going around. What's the next term? Minus V3, because I'm going from high potential to low potential. My electrons are losing energy. And then plus I3R3. That's all equal to 0. All right, and then I can also write the junction rule. I can just pick any junction and say the incoming currents are equal to the outgoing currents. Now notice I have I1 going here, I2 going there, and I3 going there. So what is my junction rule going to look like here? What are my incoming currents? Huh? I don't have any incoming currents, right? So I'm going to have 0 equal to I1 plus I2 plus I3. But that doesn't make any sense, right? Or I can't have a junction there with nothing but currents going out. So how can you explain that? Right, one or more of the directions of the current that I've chosen are wrong, because I just choose these, I don't put any thought into it, I just choose a direction for the current. And then when I solve these equations, I'll find that one or more of these currents is wrong. So that I'll have a negative number and two positive numbers, or two negative numbers and a positive number that will all add up equal 0. That'll make this true. All right. So we use these rules just to write the system of equations that we can solve in order to find the current. All right. Let's try this one. I want to know the current through each of these resistors. I want to write the 3 equations. If I have 3 unknowns, which is what I have here, I'll just write 3 equations. Your first job is going to choose the currents. There are 3 distinct currents. I'm going to choose the directions for us, and then I'll let you write the equations. I'm going to choose I1 to be right here, I2 to be right here and in that direction, and then I3 to be in that direction. So I1, for example, starts here, goes around, travels between junctions. I2 travels only along that branch, and then I3 goes there and travels up through that branch. All right, I want to write equations for the upper loop. the lower loop, and the junction. So write equations for the upper loop, the lower loop, and then the junction. One of the junctions. There are two junctions. They should both give you the same equation. Then if you flip one side to the other. Write the upper equation, the equation for the upper loop, the lower loop, and then the junction. I'm going to go ahead and start the upper. I'm going to start right here and go in this direction. So I'll get 6 minus I2 plus 4 minus 2I1. That's equal to 0. You'll get something similar for that loop. Right, so yours might be reordered a little bit, but you should have the same elements. Or you might even have the same, but everything is the opposite sign. Like you could have -6 plus I2 minus 4 plus 2I1. But depending on what direction you choose. So if I go in this direction, I get +6 because I'm going from low to high, minus 1 I2 because I'm going with the current, plus 4 because I'm going from low to high, and then minus 2I1. I1 here because I'm in this part of the branch that has the current I1, and negative because I'm going with the current. So if I chose a different direction, for example, if I went in this direction, so we might have done that, we get plus 1 I2, minus 6, plus 2I1, minus 4, which will be that equation, just everything negative. Anybody do that direction instead? All right, well, let's do the next loop, the lower loop. And just to be all on the same page, let's do the lower loop. And we will start right here and go in this direction with the current. So go ahead and write the equation for the lower loop. Your first element is going to be 6 plus 6. Because I'm going from that battery low to high potential. You'll follow it around, coming up back to where you left off. So we got +6. What's the next one? Minus 1 times I2, right? And then what do we have next? Minus 2. That's all equal to 0. And then I want to pick a junction. I can pick any junction. Say this junction right here. I have a current there, I1. I have a current there, I3. And I have a current here, I2. So what's my IN? I2 equals I1 plus I3. Alright, so now I have a system of equations. This is a pretty simple system of equations. On your homework, you have a more complicated system where each equation has 2 unknowns in it. But this one's really simple because one of these equations only has 1 unknown. So it makes it really easy to solve. Alright, you solve these by substitution is usually the way we do it. I'm going to call this equation 1, this equation 2, and this equation 3. You will have to do this for the exam. It'll be something similar to this, similar difficulty, where you don't have to go through the full blown out substituting 2 equations into 1, which is usually how we have to do that, and that's the way your homework is. But as I said, this one's made a lot simpler. So if you have it on the test and it just seems really complicated, it means that you chose the incorrect equation. So for example here, if you use the upper loop and the outer loop, then this would be a more complicated system of equations. Like if here instead of the lower loop, we chose the outer loop, or would we be able to solve that? Right, that's what we're about to do, yeah. So I'm going to solve for I2 here. So solving this by substitution, solve equation 2 for I2. And I get I2 is 4 minus I2 equals 0. So I2 equals 4 amps. And then I can plug that into equation 1. This equation 1, 6 minus I2 plus 4 minus 2I1 equals 0. So that is solving equation 1. That's these two cancel. I'm left with 6 equals 2I1. So I1 equals 3 amps. So this is just solving equation 1. And now that I know I1 and I2, I can just plug those into the junction rule. I have I1 plus I3 equals to 0, or excuse me, equals to I2. So I'm looking for I3, which is going to equal I2 minus I1. What's here? 4 minus 3 equals 1 amp. So those are my three currents, I2, I1, and I3. That's a pretty simple system of equations. You can also solve this by Gaussian elimination. I think we did this last semester. Did we do it? Yeah. Right, just happen to pick the right direction. Right. Although you might have been able to intuit the directions. Maybe. Yeah, you could probably look at it and tell. But it's not only dependent upon the resistors, on the batteries and the size of the relative size of the batteries, but it's also dependent upon the size of the resistors as to what direction the current goes. So don't try to reason out the direction of the current, just pick something random. The important thing is, though, that you realize that there are three different currents. I have one current in this part, one current here, and then one current here. Right, so three distinct currents in three distinct parts of the circuit. All right, we can also solve this. Yeah, Gary?
So on the exam, is our final answer going to matter if it's positive or negative?
It will matter. Here, when you give your final answer, you will say I1. Let's say we found I1 to be 3 amps. So you'd say I1 equals 3 amps counterclockwise. I'll ask not only for the magnitude, but the direction. I2, which we found to be 4 amps, you would say it's equal to 4 amps to the right, and then I3 would be 1 amp clockwise. So you'd give the direction and the magnitude.
And we know that they're all right because they're all positive.
They're all positive, right?
So what would we do if we come to one that's negative?
If one of these came out negative, say for example, if I3 was negative, then you would just say I3 is 3 amps in the clockwise direction. Or whatever opposite is of what you found. All right. Also on the exam, you'll be able to solve these by Gaussian elimination. I have a couple or 3 extra points for that if you do it. It won't be required, but it's a very useful thing when you're solving systems of equations to be able to solve them by this matrix method. I think we did this last semester, did we not? We did 1. Yeah, so I don't know if anybody did it on their exam for extra credit, but you'll be able to get a few extra credit points if you solve your system of equations by this method. The way you do this is you put your equations 1, 2, and 3 into an augmented matrix. So if I write equation 1, I would write it like this as negative 2I1 minus I2 plus 0i3 equals negative 10. That's equation 1. This is equation 2. 0i1 minus i2 plus 0i3 equals negative 4. And then equation 3, that's from the junction rule, is 1i1 minus i2 plus i3, and that's equal to 0. All right, and then we take the coefficients of each of these. We can write a matrix: negative 2, negative 1, 0, negative 10, 0, negative 1, 0, negative 4, 1, negative 1, positive 1, 0. This is called an augmented matrix. It's augmented because it has this extra column on the side. And if we put this in the form of an identity matrix, then the column, that far right column, will be the solution to each of the variables. So we want to get it into this form of 1, 0, 0, 0, 1, 0, 0, 0, 1. This, right, linear algebra. So this is called an identity matrix, and it would tell us then what is I1, what is I2, what is I3. This seems kind of arduous, right? Because the substitution is really easy to solve this system of equations, but when you have a lot of equations, you can't really solve them by substitution. But this is easily programmed, the algorithm for this, to create the identity matrix. It's easy to program, and so you can solve a million by million matrix. Say you have a million or a billion equations, then you can solve for all the unknowns, which isn't unheard of. Like especially today when you do a lot of simulations. Say you're doing, I don't know, mass infall or a structure that has a lot of different variables, then you might need to solve for all those different variables, in which case you'd do it by this way, by setting up a system of equations and then solving for all the unknown variables. You can't do it by hand, but you can do it with a computer pretty simply. All right. There are a number of rules here. You can multiply, let me just sort of outline the rules. You can multiply a row by a constant. You can replace a row with that row plus or minus another row. I'll show you what I mean by that. And that's it, I guess. Yeah, so you can multiply a row by a constant. That means you can divide or multiply it by a number, and then you can also replace a row by adding it to another row. All right, so again, you're not being required to do this on the exam, but once you get the hang of it, it's pretty easy. You just have to know these two rules, and I'll give, say, 3 extra points if you solve this system of equations by this method. All right, so here, I would replace row 2 with row 2 times negative 1. So I'm going to replace row 2 with row 2 times negative 1. So I'd have this, negative 2, negative 1, 0, negative 10, 0, 1, 0, positive 4. All right, so I already have my first row in the identity matrix form. Then I can replace row 1 with row 1 plus row 2. So I'm going to add row 1 and row 2 and replace row 1 with that. So this is going to be negative 2, that's negative 2 plus 0. What's the next column going to have? 0, right? I add these two numbers. 0. Negative 10 plus 4 is negative 6. You probably see the next step. What's the next step I want to do to row 1? Not multiply, but multiply by a half, by negative 1/2. So I'm going to multiply row 1 times negative 1/2. And that'll give me 1, 0, 0, 3, 0, 1, 0, 4, 1, negative 1, 1, 0. Alright, so I already have answers for I1 and I2 here, which I've already found by substitution. Alright, y'all hang on just a few more minutes, okay? Just a couple more steps. Alright, now we're going to replace row 3 with row 3 plus 2. If I do that, I get 1, 0, 0, 3, 0, 1, 0, 4. And I'm going to replace row 3 with row 3 plus row 2. So I'm adding these numbers. So I'm going to get 1, 0, 1, 4. Let's see. 1, 0, 1, 4. I'm almost there. I just have to get rid of this one in this column to make an identity matrix. And, that's right. I'm going to replace row 3 with row 3 minus row 1. And that'll give me my identity matrix. 1, 0, 0, 3, 0, 1, 0, 4, 0, 0, 1, 4 minus 3, which is 1. That's my identity matrix, and that gives me I1, I2, and I3, which we've already found. All right? So a simple Gaussian elimination to create that identity matrix. This process is called Gaussian elimination. And we've done it by hand, but it's really easy to program with an algorithm. If you go out, you can look online. There are all sorts of JavaScripts where you can do this. You can put in a 10 by 10 or 20 by 20 matrix. Yeah?
Now, show how you got, like, after the first row, the first one you did, how you did all the other ones, but how did you choose to multiply on the first one, how did you choose to multiply by negative 1? Because you're going to give them this like row 2, you made it row 2 times negative 1, well maybe 2. Maybe.
Oh, I just did it because in row 2, it was almost in the identity form.
Oh, okay.
But it was 0 and negative 1. And this
number has to be closest to the identity.
You can also move rows around. So like if you have a 0, 0, or like say a 1, 0, 0 in the third row, you can replace row 3 up to the top and then bring row 1 down.
So that would be the third rule.
Right, yeah, you can move rows around.
With the I equal 2, so like row 3 is still I3, so when you move to the top, it's still I3.
That's right. So like I could take this row and move it all the way to the top, and then take this row and move it all the way down to the bottom. I can switch them around. I can write my equation for that I want. Alright, so it might take a little bit longer, but I'll do 3 extra points. 3 extra points? Is that enough incentive for y'all to do that on the fence? 5 points? 50 points.
Yeah.
I'll do 5 points. We'll do 5 for the exam. I think that's worth your time. 5 extra points. All right. You have a good day.